My name is Emma Snyder, and this is Lab 4 for Physics 2211 on oscillation. The purpose of this lab is to analyze the motion of an object attached to the spring that was released from a particular position. A computer model was created for comparison. The energy of the model and the experiment are then to be graphically compared. The fundamental principle of this lab is Newton's second law and the energy principle. Also known as the momentum principle, Newton's second law can be defined using the equation shown below. This equation was used to update the speed at which the mass was traveling in the model after net force was found by adding together all the forces acting on the mass. The position update formula is used as well. After finding the new velocity, you can construct the movement of the mass using the position update formula. The problem contains a spring which does not provide constant force. Therefore, the problem uses the final velocity during the time period as the average velocity using the formula shown below. The principle states that the change in the energy of the system is equal to the total work done on the system. The system in this problem is defined as the mass, the spring, and the earth. Therefore, there are no notable surroundings, and the work done will be zero. This results in the following equations. Delta E equals 0 because there is no work. Therefore, the energy of the system should be conserved, and there should simply be transformed between kinetic, spring potential, and gravitational potential energy. In this lab, the model and the experimental results were only slightly different from one another in appearances. However, it is easier to see the difference in both the x and y directions. The model also shows a perfect conservation of energy, but I believe the reason for the aforementioned differences is that the energy in the experiment is not conserved perfectly. I chose to use Newton's second law because it allows for easy construction of a model as long as one knows the forces acting on the system. In this case, there are only two forces, and therefore the total net force is easy to determine. The energy principle is very useful in this discussion because it can help to explain some of the differences in the motion between the experiment and the model. For the Newton's second law portion, the system is said to be the mass and the surroundings are the earth and the spring. For the energy principle portion of this experiment, the system is said to be the mass, the earth, and the springs, and there's no surroundings. The origin is set to the motionless attachment point of the spring, and the axes are tilted at an angle of 0.5 degrees. The initial position of the mass is negative 0.128 meters in the x direction and negative 0.638 meters in the y direction. The initial velocity is 0 meters per second. The mass is 0.402 kilograms, and then the spring constant of the spring is 6.83 newtons per meter, and the relaxed length of the spring is 0.123 meters. All right, so here we can see that the origin is at the fixed attachment point and that the axes are slightly tilted. And then you can see when I press play that the motion, it starts at, with a velocity of 0 and it goes through the oscillations. And over here on the graphs, you can see those oscillations in the x and y directions. So this is the code that was used for the model and for analyzing the actual experimental data. We can see here that this is the mass, position, and velocity all being established, delta T being established. Down here, all of the conditions of the spring are being established, and this is the initial energy section, these 4 lines. And then down here, you can see the different forces being calculated, and then the velocity and position update formulas being used. And then down here, we also found all of the energies all over again and the changes in them. This is the program as it runs. The blue ball is the model and the red ball is the actual data. You can see that they're actually pretty close together. The red one skips a little bit, but we expect that to happen due to the way that it's inputted. Down here, you can see the change in energy of the model, which you can see it stays at 0 for the total energy. And you can also note that when there's one that's going higher than the other one goes lower in order to even out. So the total energy change always stays at 0. Down here, we also can see that the x position versus time graph and the y position versus time graphs, that the model and the experiment are somewhat close together, especially towards the beginning, but they drift apart, especially towards the end and peaks and valleys and stuff, especially in the y position graph. While the model and the experiment are very similar, there are some obvious differences between the two. These are most likely caused by the energy principle. The model assumes that the work done by the surroundings is 0, but in the real world, there is the drag force, which counteracts the movement of the weight as it goes. In addition, the model assumes that the spring is massless, which it is not in the real world. This may impact the Newton's second law portion of the lab, as the mass that is used in the velocity update formula is only the mass, not the spring. Some error was obviously due to issues with my analysis and the movement of the mass. For example, it is possible to see breaks in the curves in the position graphs. While the weight didn't jump, it is possible that I accidentally misplaced the point mass while conducting the analysis in Tracker and therefore created some error in my experiment. In the model, the energy principle is absolutely satisfied. Every change in energy is aligned with an equal and opposite change in another kind of energy. This caused the total energy of the system to be zero, as it should have been because there was no work from the surroundings. These are my estimations for the x and y direction oscillation periods. They are very similar and indicate that the first few times the spring goes around, it will appear to almost end up in the same spot it started in. However, these differences will start to make a bigger change towards the end, leading to the pattern observed early in the model.